Okay, so today we're going to try to go through CTV and then timeout trees. And this is going to be for mids. So it's not really aimed at the experts, although if experts want to watch and tell me what I'm doing wrong, if I'm doing anything wrong, if I have any misunderstandings, that's great. Um, my observation and frustration over the last year or two in the discussion about CTV is that it's either very hand wavy and then jumps into these kind of hyperspace, uh, very complicated scaling um, solutions. And I've always felt like I've sort of missed kind of what's going on at a very basic level. Um, so I'm going to try to go through what what these things are at a very basic level, and hopefully this will give you a reasonable model of just kind of how these things work. And so if next time you're in a Twitter spaces and everybody's sort of nodding along, you can sort of nod along knowing what these things mean. Okay. Okay, so CTV. Um, now I guess I can assume maybe you have some familiarity with Bitcoin script. I'll try to, if not, I can describe this a little bit. Um, each, yeah, let's talk about script first. So basic script. So each UTXO is a locking script. And so to spend it, you provide the unlocking script. And so what these do is, it's a secret, it's a sequence of operations which are allowed. And so there's very few operations which are allowed in this Bitcoin script. The typical ones you might use are check signature. So the basic unlocking script would be say Alice pub key, public key, maybe a hash of it or something, and then op check sig. And so this would be the locking script for a transaction. And so I'm going to call this Y, and then I'll let X be Alice signature. And then, so X, Y concatenated together. Um, this is going to be a script. Well, it's of course this here, and then this here, pasted together. Okay, so now you have three operations in the script. And what this does is it pushes this script, this XY script, pushes signature stack. So yeah, you have this stack. And so the stack, you have the signature is going on the bottom. That's step one. And then step two is you're going to push, this is one, this is two, you're going to push the public key. And then step three, this is with the check sig. Check sig, this is an operation. It's like a function that runs, it takes information from the stack. So it reads top to elements on stack. And it also reads information. And this is one of the things I was a little bit confused on, from the transaction context. So this is a word which I didn't realize exactly what it meant until recently. I guess I should say, thanks to I've gotten feedback from Polly D, Moonsettler, Shinobi, that have kind of helped clear some of this stuff up. So there's a transaction context, and the context, this is going to be the relevant information of the larger transaction. So you have I'm trying to create a transaction, Alice is trying to spend a transaction. There's going to be the input transaction is going to be loaded into the context, and this is kind of like static data. It's not going to be loaded onto the stack, but it's part of the context. So you have this input information, you have the output information. This is all something which these opcodes like check sig can access. So check sig is going to access the transaction information, and it's going to look at what the signature should be, or it's going to it's going to check that the signature is correct. So you can't know the signature ahead of time, of course. Only Alice knows this. But the signature, together with a public key, together with the transaction information, can all be valid. And then if all good, it evaluates to true. So then if this little script, this little XY script, evaluates to true, then the Bitcoin compiler says, great, whoever provided this unlocking script in this transaction now can spend it to the output that they are also providing in this transaction. So now there's a new output. The new output is just a new locking script. And this can be some sort of thing with, Bob's public key and then check sig, or it can be more complicated. There is the nice thing about this script is you can actually add some paths. Like you can make these scripts can be so that the scripts can have, can do logic where you have multiple ways to spin. You can spin it to Bob, or you can spin it to Charlie. You can spin it to Bob after 8 days, or you can spin it to Charlie right now. You can spin it to Bob after 8 days if he provides a secret key, which would be hashed, something like this. There's all sorts of things you can do so that multiple paths different ways to satisfy it. Okay, so this is just review of kind of the basic of scripts. And if you're reading, if you say think you're going to understand CTV and you go to the GitHub and it's like describes this basic or the BIP, BIP 119, it describes, well, okay, check if there's something on the stack, and then check that this thing on the stack matches the hash of the template. Okay, so that seems very basic, but it's not 100% obvious what it does. So I'll try to explain a little bit what that does. So, the basic CTV lock script, kind of like your raw thing, is going to be some hash, which you know, and then opctv. So typically what you would do is I say, this is a very basic script, not particularly useful. I want to send Alice 1 Bitcoin, but I want to maybe, I don't know, do it via CTV for no particular reason. This is just to demonstrate at a very basic level. And so I have 1 BTC in a UTXO. So what I do is I compute the transaction. Which, sending Alice the Bitcoin. Then what I do is I run this template hash, right? So this is going to be information from the transaction that is going to be hashed. And so it's one of the things which was confusing, is what exactly this information is. So what this information involves is the output numbers. I mean, the output, the number of inputs. It does not involve like the precise input transaction. It only involves the output, or it only hashes the output. So what I get is I get a hash, and then I'll call this H, and then I publish H opctv as lock script. So then if I actually have to know ahead of time, in order to spin this, I actually have to know what the transaction is, but not precisely. And that's kind of a complicated thing, is in order to spin this to Alice, she provides a transaction with her output, and this hash this will hash to H under the opctv. Right, so I could, the unlocking script here is H, and then I have opctv. This just runs like this thing just runs inside the context of the transaction. So I want to send the transaction to the compiler. What the compiler is going to do is it's going to run this, and it's going to check if it gets you the correct hash, right? And so this here is accessing, it's accessing again information from the context. And then creating a hash from it. And then checking if this hash is H. If the hash is H, return true. or evaluate to true. And then I guess because it has a verify. So verify is this little extra thing that if it fails, it's going to return the whole script as false. It's not just going to evaluate to false, it's going to actually make the script invalid. Just return it, the whole thing fails. Okay, so once again, the important the takeaways from this, which are not so obvious to me at first. One is that the set of transactions satisfying this, satisfying the app CTV, are not unique. This is this is something which confused me for a while because I had a lot of people saying, well, it defines the transaction. No, it doesn't define the transaction. It specifies the outputs. Um, it specifies the nlock. It specifies the number of inputs. Actually, I forget if this is it, but these are the main things. But it does not specify the input transactions. So this means you can spin it to the same output using lots of different possible inputs. So, just kind of like sort of a basic example. You could do like a sort of very basic GoFundMe. I guess this would be a GoFundMe with you get your money back if not everybody commits. Like say we need 10 Bitcoins for whatever we need, but 9 Bitcoins is not enough, so we would want to make sure and get commitments from everybody. And we don't want to just send them to the address. We can commit to sending it and then give ourselves a way to get to get the transaction back. So if say 20 people agree, kind of, I don't know, say they have a discussion. Each send 0.5. What each could do is to say, create a script with two paths. And I won't describe how these paths work. But one, spends 0.5 to, I'll just call this, address A to A via CTV, provided the transaction has 20 inputs to the same output A. And then what you want to do is you want to have a kind of a default situation is after I don't know, say 2 weeks. Can spend back to yourself. Or wherever else. I guess you just need to provide your own signature, and after 2 weeks. And then so the idea is everyone can send these, if 20 people were to each send this CTV locked transaction, you could take all 20 of these, and they would together be valid to give address A 10 Bitcoins. But without all 20, without the 20 different inputs, it would not be a valid transaction. And so then everybody would be able to spend their transaction back to themselves after 2 weeks if this thing fell through. Just kind of a quick note that I didn't realize, it took me a while to realize, maybe this is just me. Nlock, yeah, maybe this is obvious to some people, but not to me. So you may know that in the Lightning needed this check sequence verify. So the check sequence verify is something which happens inside a script, usually inside of a path of a script, which unlocks it after a certain time, right? So it evaluates to false if not enough time has elapsed. Nlock is kind of outside the whole transaction. So you can put an nlock time on the whole transaction, on the whole output, and it won't even run. But check sequence verify is something you can it's an opcode, which goes inside any of these script paths. This is something which I didn't fully understand until recently, when I was staring at this CTV and say, why are you committing to the nlocks if the output should also contain the check sequence verifies? Well, I guess the answer is, well, because they're different things. Okay, so now I'm going to try to give a quick overview of timeout trees, at least at a very basic level. These were a bit confusing to me. I mean, you can sort of wave your hand at them and say, well, it's a tree, but how and why and everything took me a little bit to understand. So the idea now is you have, let's say I have so the coordinator say Carol has 1 Bitcoin and would like to, just to keep it simple, create 8 Lightning channels. Now, you can always just do this, create 8 Lightning channels. But what the CTV allows you to do is, so, Carol has this UTXO, so you take the original, the funding UTXO, and it goes to this. Now, this is going to be a CTV transaction. And so this CTV can only be locked. You have to have the correct hash. This will go to, say, 2 more CTV lock scripts, each of which goes to 2 more. And then each of these, say, goes to 2 more, etc. And then if you want a little bit of extra, you could even make 1 more. Each one of these has 1 more CTV. So what does this actually mean here? This here is going to be, this is called the leaf transaction. And what it will be is going to be this is going to be a 2 of 2 multisig. which is funded by Carol. And it's committed to by the virtue of every step along this every step along this tree is committed to the next step. So if I were to unfurl this whole tree, I would be committing like unto like 16 or 32 or something, 16 transactions, 31, I don't know. But the point here is that when we're funding this channel, say this person here, we'll call this Levi for Leaf. Levi has the other signature here. They would also be provided with the hash, the CTV hash here, the CTV hash here, the CTV hash here. So if they wanted to put this transaction on chain, and they may or may not want to do this, but if Levi decides he wants to put this transaction on chain, they have this information here, so they can hash this transaction data, which is a hash itself, right? So this is going to be an op CTV with a hash. This is an op CTV with a hash. Can put this one, tells you the information they need to put this on chain, and then with this one and this one, it tells you information you need to put that on chain, and then this one and this one, put that on chain. So if Levi decides to do this, what they're going to do is they're going to first run this, and they now have enough information to get, then have these two hashes. So this becomes say this goes on chain, then to run this one, these two go on chain, and then to run this one, these two go on chain, and then to run this one, these two go on chain, and then this one just runs. And so you still actually don't even, so the reason I put this extra commitment here is so he doesn't even know, like he can unfurl this transaction, but he doesn't even know what's happening over here, right? This is just some hash. Okay, so what you get is like all of these things. I guess I didn't draw the other 8, but there's 7 of these things are not on chain. I did have to put a bunch of things on chain, but that's actually not what you want to do, because the idea is Levi now has, so he can put it on chain, which is what makes this a workable Lightning channel. Right. So the fact that Levi could put this on chain, this is a transaction. So it's a 2 of 2 multi. It's a 2 of 2. This here is going to be this 2 of 2 multi-sig, which is completely committed to, even though it's not on the chain. And this is where I think that the big the boost you get. This is the important thing. So we can treat this as an actual Lightning channel. And this is kind of the big thing, right? Without putting it on chain. Right. So each one of these folks over here, they know that their Lightning channel is there. And so now what I've done is I've created, so the coordinator here has created 8 Lightning channels, but with 1 transaction on chain. So okay. Now this, of course, this could be any number. depending on the structure of tree. So like, you can make this, I could be 1024 if you just want to have a binary tree. You don't have to have a binary tree. It could be 81 or 729, or you don't even have a tertiary tree. You can structure your tree however you want. You can make this, can make 69 497 leaves if you want, just by making your tree branch to have that many leaves. Okay, so this is where it gets kind of interesting and funny. So, and slightly confusing. The idea, or the goal, or the idea, or the hope, I guess, is that none or very few of these channels actually go to chain. So instead, you hope they get all drained. Right? So these channels are kind of funny, in the sense that, right, so Carol is setting up this channel. Let's say putting point, what I do, 8, 1, 2, 5, funding a channel. So typically, in most settings, you'd think that when you're setting up a lightning channel with someone, if you put 0.125 in and they put 0 in, then you have 0.125 and they have 0 in your sort of internal accounting, because the way lightning works is you have this sequence of internal accounting transactions, which are going to be two multi-sig transactions that you're sending back to each other, kind of signing them as you go with the latest state. So you would think most cases what you put in is what you start with. But my understanding for this is that actually, Levi starts with a balance. In the initial funding transaction. So then Levi would want to spend this. And presumably Carol is very well connected to the rest of the Lightning network. So then Levi could spend this wherever he wants. So what this implies, and this is, to me, the only thing that would make sense, is somehow Levi is providing Carol some funding some other way. Like, I don't know, maybe this is Carol is actually PayPal or Bank of America or something, and is setting up Lightning accounts for customers. So, Levi would transfer in $100, and Carol would open up this virtual channel where Levi now has $100 in Lightning. And then Levi can spend it anywhere in the Lightning network. Okay. So this is kind of the basic idea. Of course, if Levi wants to just cash out, Levi would have to post all these this chain of CTVs all the way, would have to post all these transactions. And so then now he has an actual like on-chain Lightning channel, and then he could do the things like force close or whatever, or cooperative close or whatever after, the typical lightning things after this has been pushed to chain. But Levi could just spin the entire balance and go about right. Levi gets $500 in Bitcoin, spends it on the Lightning Network. So this is now it's back to Carol. But the question now is, what does Carol do with this? So in order to reclaim this, to reclaim, she needs to put it on chain and close the channel. Okay, now this is where the timeout part comes in. So this is obviously very heavy, right? This stuff is heavy. Right? If all these people take their lightning, they spend it, they forget about it, they don't put it on chain. What Carol has now is one, say all 8 of them spend their 0.125 on wherever. Carol now has a whole Bitcoin, which is just locked up sitting there. And the only way to get this back is to go and unfurl all these transactions to the chain and then close them. This is very heavy. It's not interesting. It's not the point, right? It's sort of not very scaling friendly. So here's where the timeout stuff comes in handy. Look at the tree again. So you have this initial transaction. This is Carol. She's funding this UTXO, which is CTV, some sort of CTV transaction, which outputs, et cetera, et cetera. But let's say each one of these actually has multiple spending paths. So go with red because that's on the one on John Law's paper. So you have your standard CTV. Then you also have another spending path, which back to Carol after some sort of time. E. So in each one of these does this. So each transaction has 2 paths. One is the CTV to the next point on the tree. And then 2 is a return. And this is going to be a very cheap, very simple transaction. This is after E. And say, I don't know, 3 months. So this means that if nobody, and this is sort of the best case, everybody spends their balance, then Carol can sweep it all back. How, and you just do it here. I mean, actually, the first one can be, you can have it on the first one too. So she commits one transaction. So it's this transaction here, and it has if if 3 months have expired, it can all go back to her and she can recycle the liquidity, or it can go through at any time before that, you can start going through these trees. So this means that if somebody does want to actually use their, put their Lightning channel on chain, um, it means that you're going to actually have all these transactions committed to, right? So this is going to be committed to, this is going to be on chain. Um, but still, each one of these further ones, so this is still just something, it's going to have a loop back. All these are going to have a loop back, right? Except for this one here, that's going to be the one that doesn't have a loop back because it's already been spent. So everyone that's not been spent is going to be able to be swept back to Carol. So okay, I think that's clear now. So what you can do is can create, I don't know, just say nice round number, 1024 leaves each, the Bitcoin. And then if, say, 3 people put the transactions on chain, then you have this path, you have this like 10 deep path, or 11 or something. Someone is using a path, they're going to have to, like, they're going to put all these transactions on chain. But this is going to be not nearly as many. I mean, it's going to be something like, you're putting this one on and this one on, this one on and this one on, say for this path. It's going to be roughly order of sort of the depth. You say you had to put, I don't know, this might be, say, 20 transactions go on chain for each. And there might be some overlap, like if they have a common path for a little bit, you can actually get a little efficiency there. But you're talking about, say, 60 transactions that go in on chain versus 1,024. And the cleanup is still relatively cheap, right? So you're talking about, you need, say, 60 cleanup transactions, versus 1,024. And you can play with the math, and then you can um see what happens if you make these tertiary trees, or splitting them in different ways, or um you can play with the math and decide how many, if you think most people are not going to end up putting their channels on chain, um you're going to save a lot of on-chain transactions. Okay. So I think I provided the basics. Again, it's funny. I mean, the idea, this is still something which wasn't obvious to me exactly. The idea is that everyone is constantly spending, is draining or spending within a short time, so that liquidity can be recycled. Because what you don't want is, you don't want something just locked up in a Lightning channel forever, because it's expensive to unlock I mean, it's expensive to um, take the lightning channel and give yourself the funds in the channel. So, again, if Carol has everything on one side, she'd like to give herself the funds. This is expensive if she has to do this thousands or millions of times. Um, but it's so much cheaper to do it with a timeout tree. So this would, there's been some discussion. I don't know how well informed it is about this idea of everything, this rush to get back on chain with thousands or millions of transactions. And if these are working correctly, and I guess I don't have any guarantee, this is just speculation of how these would work. If these are all working correctly, um, everybody's spending their money before trying to get on chain. They're sending it to another Lightning channel, or they're spending it other ways where you can spend it. And they're not just kind of like setting up Lightning channels and then trying to, sit on these Lightning channels forever. So that's where the efficiency gain is here. I have no idea how this would work in practice, but that's a different discussion. I'll leave that to you to imagine how this would play out. Who would be the coordinators, how many people would use those, whether they would like not spending or being forced to spend in a short amount of time, or maybe that's just super easy for most people. I don't know. Anyways, I hope this was useful. If I'm wrong on material stuff, please let me know. I don't like to be spreading misinformation, unless it's something like, oh, it's actually the hash of the public key. Well, that stuff's fine. But yeah, I hope this was useful.